So, hi everyone, and thanks for coming. I hope you all had a great week. So today we have the pleasure to host Eva, who is a postdoc here at Milan and McGill with Prof. Stephen already and Tim O'Donnell. And she'll be sharing with us some thoughts on AI and cognitive science. So before handing the mic to you, Eva, let me remind you all of some house rules. As usual, clarification questions will be allowed to be asked during the talk. For people in person, you just have to raise your hand and wait for me to give you the mic so that people online can hear you. And for people online, you just have to type the word question, or I have a question in the chat. And when the time is right, I'll let you directly ask you. If you don't have a mic, please specify it in the chat so that I know that I'll need to read your question. For people online, of course, in order to ask your question, make sure to unmute yourself and mute yourself back when you're done. And remain muted if you don't have any questions, so that I'll have to do it manually. And there'll also be some additional time at the end of the talk for people to ask further questions, make some comments, or have a more informal discussion with Eva and the other people here. That's pretty much it for me. So whenever you're ready, Eva, the floor is yours.
Awesome. Thank you so much for joining in person and virtually for this talk on cognitive science and AI, neural networks for studying people. All right. So my goal for today is to convince you, hopefully, that AI models can be really useful tools to help us understand the human mind. Now, I want to show you that models can actually be part of a comprehensive toolkit that we could use to study human behaviors. And the particular behavior that I'll talk about today as my running example will be how we learn language. So why is this an interesting question? Why should it matter to you? Well, from the human perspective, learning language is a really interesting problem, right? So I'm sure many of you at some point have interacted with young children, possibly have children of your own. And if you're like me and other parents out there, you're probably fascinated just by how quickly they learn, right? They go from basically being blobs when they're born to, by the age of 3, being able to hold a conversation with you, telling you about their day at daycare. And during that time, they've seen, as little as 5 million, maybe 10 million words, yet they're still able to learn a language. If you've tried to learn a language as an adult, you just know how difficult it is. And so clearly there's something really magical going on about how we learn our first language. From a machine learning perspective, learning language is also a really interesting problem. So if you've tried to train language models, you know just how difficult it is to come up with efficient algorithms, at least data-wise and energy-wise, that can mimic this type of behavior that we know is speaking and understanding language. So though this talk will obviously be pretty heavily on this concept of learning language, I want to stress that the approaches that I'll talk about in terms of using AI and cognitive science together are applicable to any type of human behavior that involves learning or reasoning. Okay, first off, I want to ground what I mean by cognitive science. I'm sure everyone in this room is familiar with what an AI model is, but what is cognitive science exactly? So cognitive science is the study of the human mind. And by mind, I don't mean the human brain. So the human brain is, it's an organ. It has biological responses that can be measured and tested. And that's what we study in, say, neuroscience. In cognitive science, we're really actually interested in more the abstract concept of how the mind or humans encode, learn, and represent information that they see in the world. So by analogy, you might think of this as the difference between the actual weight values of your model as maybe the brain, and instead the information that those weights are supposed to represent. Or an even simpler example, the difference between like a word vector embedding versus the word it's supposed to represent. So today, we're really talking about cognitive science and the mind. Okay, so in my research, I try to bridge these two fields, right? Cognitive science on the one hand, and AI on the other, to try to study learning and reasoning both in humans and in machines. But this is a two-way street, So on the one hand, we can try to find interesting ways that we can use these models to help us study people, but also we can try to take inspiration from what we know about how people learn and represent information to help how we design our models. So the plan for today is to connect both cognitive science and AI and look at both these directions. On the one hand, using models to study people, and on the other, cognitively inspired models. I'll come back to this idea of cognitively inspired models towards the end of the talk, but I'll spend a large part of the first half really going into depth about this idea of using models to study people. I'm going to talk about two approaches to do this. One that I'll call models as tools, and we'll look at a case study around learning words. And then the other that I'll call models as minds, where we'll look at a case study about something called the shape bias. So you'll notice in the top hand corner here, we have this little tree structure that I've drawn. That's going to serve as your map as we go through the talk to see what branch we've gone down. We're going to be doing a pre-order depth first search, so going slowly down, back up, down, and back up as we go through the talk. Okay. So as I mentioned, the direction that I'll start on today and really center on is this direction where we try to use models as an object of study to help us understand new things about people. So there are many ways in which we can obviously use machine learning approaches to help us understand human behaviors. The most obvious one would be a purely methodological one where we're trying to use machine learning as a way to help us do data pre-processing or even data creation for experimental studies or something like that. But that's really not what I want to talk about today. Today is really about considering the models themselves as an object of study and then trying to map what we learn about how their internal representations and processes work to equivalent ones that might exist in the human mind. So I'll talk about two approaches to do that. As I mentioned, the models as tools and models as minds. And we're going to start with this models as tools approach. Okay, so models as tools. So I'm sure all of you at this point have probably heard of large language models. There are many different types of language models out there. And it turns out that these types of models can be super useful for studying people because these models are trained on language and text that we've produced, right? At least up until now. So one of the ways that's been super fruitful for using these models to study people is to actually study their word embeddings. So word embeddings are these vector representations in continuous space of the meanings of words that models have learned or encoded, and they encode all sorts of subtle information. Now you can actually perform operations on them and measure things like similarity or other types of relations. And importantly for us, what these AI models give us is they give us a way to extract quantitative representations for unobservable concepts, right? So meaning is an unobservable thing. It's an abstract concept that we have, yet we have a way to now represent it in a quantitative way that we can actually operationalize, right? So, using word embeddings, we've been able to measure all sorts of different human behaviors and concepts, things like social bias, right? So we found in research that models reproduce our gender biases, for example. And so we can now use them as a way to measure certain biases that might exist in society. They also reproduce things like word associations or what you might think as mental maps of how we might organize related information. And even they allow us to measure things like cultural shift, so how different concepts in society may change over time. So in this models as tools approach, what we're doing is we're extracting some kind of representation from our models and then using that as a way to approximate an abstraction that we think also exists for people. So in the examples I just gave, we're using word embeddings from a model as a way to approximate this concept of word meaning. Now, I'm going to give you another concrete example from my own work where we'll look at another type of approximation that we can use and a specific behavior, which is learning words. So to introduce this behavior, we're going to do a little mental experiment. And imagine that we are all language learners learning our first language for the first time, and we're on a walk with our parent, and suddenly we see this creature run by, and our parent says, "Gavagai." So in theory, this is actually, our job as a language learner is to figure out what that could possibly mean, right? And in theory, it's actually not that simple, because this could mean a whole slew of things. It could mean rabbit, it could mean white rabbit, it could mean look there, or wow, or careful, right? It could mean all sorts of things. Yet somehow we figure it out. We figure out what that's supposed to mean. And so clearly, there's more going on than just simply getting all of this information from the world. We are selectively choosing information in some way, be it unconsciously or consciously. And so in my research, I try to understand what information learners are actually paying attention to when they're trying to learn new words. And that's what we're going to try to figure out, is what type of information kids are tracking. Okay, so to situate this particular project, I'm going to start by giving you a couple facts or information we already know about how kids are learning words. So for one thing, a cool fact is that kids are actually super consistent in the order in which they learn words. So kids will learn, and start saying a word like milk before they'll ever say a word like sad, and this is true cross-linguistically, okay? And this, at least we know, seems to correlate with the fact that words are either more abstract or more concrete, where like milk is a very concrete word, it's something you can point at in the world, whereas sad is a much more abstract concept. But also, it has to do with statistical patterns. So we know that a word milk is super frequent in kids' input, much more frequent than a word like sad. And so we know that kids are both consistent and statistical learners. But in this particular project, I wanted to see if we could push that statistical learning beyond frequency, and whether or not we could look at whether kids were actually tracking the words in the context in which they appear. Did conditional probabilities matter? So my research question was, are more predictable words in linguistic context easier for kids to learn? Or are kids, like language models, paying attention to the order in which words appear to try to learn them? So here we have these two, abstract concepts that we have to find quantifiable ways to measure, right? So what it means to be predictable and what it means to be easy to learn. So let's start with ease of learning. So ease of learning, pretty simple. We're going to say that ease of learning is equivalent to what's called age of acquisition. So we're going to make the assumption that if a word is easy to learn, it's learned early. Okay, so age of acquisition is the age at which 50% of kids are reported to be saying a word. For example, the word milk, by about 13 months, 50% of kids are able to say that word. And so that's what we'll use as our measure for ease of learning and what we're going to try to predict. What about predictability? So this is where language models are going to come into play. We're going to try to equate the predictability of words for kids to the predictability of words of a language model. Now, we all know a language model is only as good as the data you train it on. And so we want to make sure to train our language model on data that resembles the type of language that kids are actually exposed to. So we're going to try to build a corpus of child-directed language, so examples of what kids are actually hearing. So we'll train our language model on data that we extract from a really cool resource called the Childis database, which collects, among other things, transcripts of child-caregiver interactions across many different languages and many different studies over the years. And from that, we're able to extract a corpus of all the sentences that are said to a child or around a child, but not by the child. So representing, a comprehensive estimate of the type of language these kids are being exposed to. We do this for 5 different languages: English, French, German, Spanish, and Mandarin. We train a bunch of LMs on it. Okay, so now we can be a little more precise about our research question and say, are predictable words for a language model trained on child-directed language learned earlier on average by kids? Okay. So the LM that I'll be using in the particular examples and results I'm going to be showing you is just going to be a 2-layer LSTM, but as I'll mention at the end, we've done these experiments with other types of language models, including n-grams and transformer-based architectures. Now, the nice thing about an LSTM is that it's a type of recurrent neural network, and what it gives us at every state, right, is it gives us the conditional probability over next word at that current state. So if we were, trying to process the sentence, is that a bird, by the second state at that, what our output layer gives us is the conditional probability having seen is that of the possible next word. And so from that conditional distribution, we can just extract the particular probability of the word we're interested in. So these models are actually, designed to give us those conditional probabilities. So how do we go from these models to actually determining this measure of what it means generally to be predictable? So if we look at an example, what does it mean for the word dog to be predictable? So the way that we measure predictability overall is we're simply just going to extract all the sentences in our corpus of child-directed language that contain the word dog, and then give those to our model, extract the particular probability of that word in each of these contexts, and average across all the contexts in which we see that word. Now, the last thing we're going to do is we're going to take the negative log probability of that word, so of that average word. So the reason we do this is not just because working in log space allows us to represent these smaller probability quantities in a better way, but also because negative log probability is actually something called surprisal. So surprisal is a measure in information theory of the amount of information that's encoded in a certain outcome. And it turns out that it's actually a really good measure of human processing difficulty. And this has been shown in a bunch of different studies. So one thing to note, though, is if we're going to be using surprisal, we're going to kind of be flipping the sign on what we mean by predictability, where something that is highly predictable in terms of its probability and context will have very low surprisal. It won't be very surprising as a possible outcome, whereas something that is not very predictable in the context it tends to appear is going to have very high surprisal. So it's going to be something that is very surprising or not a likely outcome. Okay. So the final thing I want to talk about before I show you results is this notion of lexical category, because we're going to look at results by a lexical category. So to make sure we're all on the same page, lexical categories are these categories of words that are based on what you might think of as their function in language. So you should all probably be familiar with what a noun is. So nouns are kind of like variables, right? They tend to have reference and they map to some kind of referent. Whereas predicates, these are things like verbs and adjectives, will mark relations, right? They'll mark relations between nouns or mark states on nouns. And then finally, we have things like function words. So function words are these little grammatical words that you see all over your language. These will be things like prepositions like inside or behind, but also quantifiers like more and connectives like and, or, and even pronouns. So you, me, and so on. Okay. So our question was, are more predictable words for a language model trained on child-directed language learned earlier on average for kids? So really what we're trying to do is predict this age of acquisition based on surprisal. So we can look just quickly at some example words of that relation, just to kind of give you a sense. So we'll look at some examples from Québécois French. So these are nouns in Québécois French. And on the x-axis, we have language model surprisal. It's been, and then on the y-axis, we have the age of acquisition in months for these words that are reported. So we have that lait there, or milk, right? Learned really early, tends to not be that surprising in the context in which it appears. But then we also have things like loup or ours, so wolf or bear, that are learned much later than milk, but also tend to not be that surprising in the context in which they appear. What about verbs? So if we look at verbs, a bit of a different picture is showing up here, right? Where we have verbs that are learned very early, like tomber, to fall. And then we have verbs that are learned much later and tend to be less predictable, like choisir or penser, choose or think, that appear much later in language. And then finally, function words, encore, a classic, learned very early by kids, and tends to be pretty predictable. But then you have things like même or pronouns like vous that tend to be learned later and not as predictable in the context in which they appear. Okay. So I'm going to show you some results. So we want to fit these linear models, right, where we're predicting age of acquisition based on surprisal. We do leave one out, cross-validation across all of the words we've got. But really what's important here is we're going to be looking at the relationship that exists between these two. And we want to make sure that it is a positive one, meaning that we expect to see that words that have low surprisal or are generally very predictable should be learned earlier, are easier to learn, and words that are have high surprisal and are therefore harder to predict in context should be learned later. So we're looking for positive coefficients. At least that's what we'd expect to see. So let's look at some results, again, for Québécois French to start. So I'm going to compare it to unigram surprisal, which is frequency. which we know does predict age of acquisition, just to give us a bit of grounding. So let's start with nouns. So what do we see? So in the case of frequency, nouns have a positive a coefficient estimate for unigrams appraisal. This means that nouns that are more frequent are going to be learned earlier than nouns that are less frequent, as we'd expect. But in the case of our LSTM appraisal, we're right on that zero line, meaning it's not predictive for the age of acquisition of nouns. What about function words and predicates? What happens there? Here, we see a really different picture. So here, actually, surprisal does matter and is a good predictor of the age of acquisition of these words, so verbs, adjectives, and these little grammatical words. Here, predicting, keeping track of the order in which these words appear during learning seems to matter. And it turns out that this result holds across a bunch of different languages: American English, German, and actually a whole slew. So I'll give you a list here. American English, British English, Australian English, German, European French, Quebecois French, European Spanish, Mexican Spanish, Beijing Mandarin, and even Taiwanese Mandarin. It even holds, at least for English, when trained on the BabyLM challenge corpus, for transformer-based models like OPT, Roberta, and T5. Okay, so what have we learned? So are more predictable words in linguistic context easier for kids to learn? Well, the answer isn't that simple. The answer is yes, it seems to be the case for things like verbs, adjectives, and function words, but no for nouns. So why might this be happening? Well, verbs, adjectives, function words, as I mentioned, these are kind of words that represent relations, right? They're almost like functions. And so to get their meaning, you actually have to kind of consider the context in which they appear, the other words they appear with. Whereas nouns, at least the nouns that kids are going to hear early on in their lives, are going to be really concrete things most of the time that are going to have reference in the world that they can experience through other types of input, be it visual, just seeing an apple on the table when the word is mentioned, or even social, like a parent pointing to the object, right? So that might be what's explaining this difference between these types of words, at least for people. So in this particular project, we use this models as tools approach, where we extracted from our model a way to measure word predictability in context from the language model. And we use that as an approximation for word predictability in humans. And doing so, with this models as tools approach, we were able to learn a bunch of really cool stuff. So humans actually do pay attention to word co-occurrences when they learn, but they don't learn all words the same way, right? Learning requires a diverse set of strategies, at least for people, and a diverse set of inputs. Okay, so that was our models as tools. Now I'm going to talk about another way we can use these models, again, as our object of study to try to understand people, which I'll call our models as mind approach. Okay. So the models as mind approach is quite different from the models as tools in that we're no longer seeking to establish this direct link between human cognition and the model, at least at first. Instead, we want to study the model on its own as our object of study, and then post hoc, once we've been able to use this model to establish things like causal relations, use it to try to hypothesize whether or not these same relations might exist in people. So I'll show you exactly how that works with a concrete example, again, from my own work. So to introduce the second behavior we're going to look at, we're going to do another little experiment. So if I tell you this is a DAX, now there's another DAX, most of you are going to assume that the object I was referring to there was this one. So this is because we have, almost all of us in this room most likely, what's called a shape bias. So the shape bias is a tendency to assume that novel lexical categories or novel categories of objects share shape properties rather than things like color or texture properties. This is a learned bias. We don't have it at birth. We see it appear in kids around the age of 2, and it persists into adulthood, as you've probably experienced just now. And it's thought to be a learned inductive bias that helps kids learn new words once they've got it. So most of the previous debate has really just been about like what strategy kids are using to learn it, but there's a sort of chicken and egg problem here, which is that it has to exist in the parent's language for kids to learn it. And so where does it come from in the first place? So that's the question I'm going to try to answer today. So how did the shape bias emerge, both in our language and perception? And I'm going to try to argue that it follows from something called communicative need. So I'll explain what that is in a minute. Okay. What?
Before moving to the next part,
Yeah.
you had a clarification question whether the difference between nouns and other words is suggesting that conditional probabilities are not a good indicator of reliability, since nouns have a much larger range of conditional probabilities.
I see the question. Okay, so yes, nouns, well, it depends on which nouns, but some nouns will they have, I guess, yeah. I'm not sure that they necessarily have that much larger conditional probabilities in the sense that, function words, for example, show up in a wider range of contexts. It's just that because they're very frequent, they'll tend to have, conditional probabilities that may be smaller. However, since we're at least controlling in this case for frequency, we'd actually expect that like function words, for example, have a larger range, at least in the language that kids are being exposed to. Because as I mentioned, these words tend to be pretty simple. Kids aren't hearing things like words like democracy or abstractness and stuff like that, right? These are things that are pretty concrete. So I'd say that I'm not sure that it's true, at least in the case of kids and the types of language that they're hearing, that nouns are necessarily showing up are having a larger range of conditional probabilities, at least in this case. It may be true though for like the types of language that like language models are being exposed to, which is a much wider variety.
So if instead of nouns versus others, you looked at closed versus open.
Mm-hmm. Yeah, so like predicates and nouns together, and then closed class words would be function words.
Yeah.
Mm-hmm. Yeah, I guess we know so function words are basically closed class words, so those we know do show this pattern. And I wonder if we were to combine the nouns and verbs, what we would get like results. The issue we run into there is that because of the databases we're working with, the list, so we get these age of acquisitions from these like parental reports. These are like checklists of words that parents fill, and they say what words their kids say. And those lists are biased towards nouns. They have a lot of nouns on them versus other lexical categories. So if we were to combine those two categories together, we would definitely not necessarily see an equivalent, a frequent, like the relative frequency of nouns and verbs in natural language versus the ones that we're actually testing. So that's one of the reasons we wanted to also keep them separate. And also just from like previous work. Yeah.
Well, you could just separate into three categories then. You could have the nouns, you could have the other content, open words, and then you can have the closed ones, right?
Yeah, I think that would be about equivalent to what we currently have, because adjectives and verbs are the other open class words that aren't nouns, and I guess adverbs. And then everything else is sort of lumped under function words right now. So the function words is pretty much maps to closed class words. But yeah, we could try that. Yeah. Yeah.
Just as a follow-up question.
Yeah, I'll go.
Just as a follow-up question to the question, do you think the amount of reasoning versus amount of memorization that's involved in encoding the word has any relationship to what we observe in humans? Because it seems to me like nouns, it's a lot more memorization than actually reasoning, which maybe relationships involved a lot more.
Interesting. Yeah, I don't know. That's an interesting idea. It's hard to say here because obviously here we're only looking at at linguistic input. And in some sense, you could argue that reasoning is involved in being able to map the different input information that's required, say, for learning nouns, like needing to map the information you're getting visually versus linguistically. And so I don't know, I wouldn't be able to tell, at least from these experiments, whether or not that's the case. One thing I can say is we do know, like in general, there's a bit of evidence for Mandarin being slightly different, but for most languages, it seems like nouns tend to be learned earlier. So we learn a lot of nouns first, and we have this like noun first bias. And then we start to learn other content words, which could kind of speak to that, where we may be using, you know, a different learning mechanism initially. And once we've developed the ability to kind of reason about these relations, that's when we start learning things like predicates and function words. Yeah. Cool. Okay, so I'll continue with this. So looking at the shape bias in language and perception, what is communicative need exactly? So to start off, it turns out humans develop solutions to communication problems that tend to fall somewhere along this Pareto frontier between information loss and complexity. What do I mean by that? It means that when humans develop languages, their languages allow them to communicate successfully without losing any information, or at least trying, or being misunderstood. So they try to develop languages that allow them to, you know, successfully talk to each other. But at the same time, they try to maximize the simplicity of those languages. So they try to be the least complicated possible, given the fact that we have limited memory resources, aka the brain, right? So languages tend to kind of try to optimize for that trade-off. We'll look at an example. So for example, how we talk about kinship systems. So kinship systems being you know, the different relationships that might exist between people in a family tree. Different languages will have different words to organize that. So for example, in English, grandpa or grandma, it's the same whether or not we're talking about our maternal or paternal side. However, in a language like Northern Paiute, there, we actually have separate terms, whether or not you're coming from the maternal or the paternal side. And so they have a slightly more complicated system when it comes to making these kinship distinctions. And so the blue dots are actually attested systems that we know exist in the world in different languages, whereas gray is the theoretically possible systems that could allow you to separate these different kinship systems. Red is English. So English is a little simpler, right? Which means it loses some distinctions. Like you can't talk, you have to add more information in order to make that distinction between your paternal and maternal side. And yellow is that Northern Paiute has a slightly more complex system and less information loss. So the reason this happens is because information loss and complexity are thought to both be modulated by this independent variable called communicative need. So in the case of kinship systems, you could think of this as like in American societies, talking about whether or not your grandparents are your maternal or paternal grandparents doesn't really matter that much from a cultural standpoint, but more maybe in societies that speak Northern Paiute, elder relations are really important, and so therefore you want a system that allows you to make those distinctions. So there's a higher communicative need to make those distinctions. So you develop a system that allows you to do that. Okay. So in order to show this relationship, this causal relationship that exists between communicative need for shape distinction and the shape bias, I'm going to try to model this process using neural agents. So we're going to have neural agents play communication games to develop languages together. And we want to see whether or not those languages end up showing these same efficient communication properties and why the shape bias might actually follow from that. So in these games, we'll have listeners and speakers, so agents will take turns. If they're a speaker, they'll receive an image of a target object. And if they're a listener, they'll receive another image of the target object and some distractors. And the speaker will have to produce some message that over time allows the listener in that particular game to choose the correct image. So in order to learn, the speaker will, every time the listener picks the correct target, get some kind of reward, whereas the listener will be able to learn simply by mapping the correct messages to the images that they choose, just using cross-entropy loss. Okay, now I talked about communicative needs, so we have to have a way to operationalize this concept of communicative need for shape distinction. So the way we're going to do that is through what I'm going to call shape games. So in shape games, at least one of the distractor items only differs in terms of its shape from the target object. So in order for agents to actually be successful at that particular game, their message has to somehow encode this notion of shape, right? So in this case, we have the cylinder versus the sphere. Both of these are purple, both of these are metallic, both of these are large. but they're a different shape. So the only way that this game could be successful is if somehow the word that the speaker comes up with encodes this notion of shape. So communicative need for us is going to be operationalized as this proportion of shape gains seen during learning. Okay, so I mentioned agents can be both speakers and listeners, and their input is images, but they're both producing messages and comprehending messages. So they have to have some kind of visual component as well as a language component. And if they're speakers, they'll use their production component, versus if they're listeners, they'll use their comprehension component. Importantly for us, they have this shared embedding space, whether or not they're speaking or listening. So that shared embedding space represents the language they're going to end up developing. If you want more details specifically on what these are, we can talk about it after the talk too. Okay. So in the game setup that they're going to have, we've got 320 unique objects that can differ in their shape, color, size, and material. We have about 33,000 images, so we have these objects randomly appear in different parts of these 3D planes. And you can see this grid here, and think of it as representing those 320 objects. It's 320 little squares. So the goal of the agents really is to come up with some kind of optimal partition of this space, where each one of these spaces or these colors represents a different word to refer to those objects. So, in English, we don't have a separate word for every apple, right? We have a word for apple that represents these sort of shared features, and anything that fits in that category is going to be called an apple. So the same thing is happening here with these agents. They're trying to find words that represent shared feature spaces that represent a specific category of objects. Does that make sense? So they're coming up with a language. That's what they're doing. Okay. So the independent variable we're looking at that we're going to try to modulate is this communicative need for shape distinction, right? So we're going to change that proportion of shape gains. And then what we want to see is how that ends up affecting our dependent variables, information loss, and complexity. So we'll look at some results. So on the x-axis, we have communicative need, right? We're at 0. That just means we're randomly sampling games. Some of those could be shape games, so those will be color games. Some of them will you can talk about anything, it doesn't matter. All of the objects are different. Whereas at the other end of the spectrum, at the 40% mark, that means 40% of the games are conditionally sampled such that they are shape games. So there's likely a higher need to make those distinctions in that communication setup. Okay, and then on the y-axis here, since we're talking about informativeness, we're just simply going to have accuracy on games. So how accurately do they communicate? Are they able to communicate successfully, or are there games where they're losing information along the way and they're being misunderstood? So let's look at some results. Okay. So what I'm plotting here is their accuracy on shape games. So their ability to make shape distinctions. Are they losing information in their system when they have to make shape distinctions? So initially, they're not very good at making distinctions based on shape when you force them to. But as you increase that need to communicate about shape, probably not so surprisingly, they end up developing systems where they get a lot better at making shape distinctions. So I also plot just the overall accuracy over games because you'll see it dips a little bit there, in part because shape games are actually really difficult for these agents. Their visual components are CNN-based, which tend to have color biases, and shape is a little harder for CNN. So when you force them to do more shape games, overall, they're going to do a little worse. But you still see that they have that increase in specifically in the games where they have to talk about shape. So the same thing happens to complexity, where complexity is this mutual information that exists between that embedding space, their language, and the labels that we have for these images, the types of features that are actually encoded in these objects. And so as we increase that need to communicate about shape, they also develop systems that are much more complex in terms of the distinctions that they make about shape. And so really cool, actually these agents, like us, develop systems that fall along this Pareto frontier. So they are also optimally efficient in the languages they develop. So each of these colored dots are actual experimental runs where, based on different communicative needs, they've come up with languages. And the gray dots are theoretically possible languages they could have come up with. And so agents really do fall, like us, along that distinction, so along that proto-frontier. Okay, so at this point I've shown you that agents, these neural agents we're working with, are also optimally efficient communication designers. But why the shape bias? Why does the shape bias follow from this? Well, if we look at what happens to other featural spaces, like for example, color, as we increase this need for shape distinction, we see an interesting pattern. We start to see this trade-off where initially, when we're just randomly sampling games, agents actually have kind of an innate color bias where they like to develop systems that make color distinctions just because it's a very localized feature, so it's very easy for them to encode. But as we increase that need to make shape distinctions, their performance on color games starts to plummet. And the same thing happens in terms of the complexity of their naming systems and their ability to make those distinctions. And so what's happening here is that shape and color are two dimensions of the same referential space. We're still talking about those 320 objects, right? And so as we increase the need to communicate about shape distinction when we're talking about these objects, we're actually consequently decreasing the need to communicate about things like color. And so over time, what you get is you get a shape bias that emerges. Okay, so at this point, I've shown you that agents are efficient communicators and that the shape bias emerges because of a communicative need for shape distinction. I haven't said anything about people though, right? All I've done is I've shown you that this is the case for our neural agents. So what about the real world? Is there a reason for us to believe that humans also have this high communicative need for shape distinction? Well, one of the reasons we might think so is because of what we call artifacts. So artifacts are man-made objects. And one of the interesting properties of artifacts is that often their shape is what we'd call an affordance, meaning that their shape encodes their use or what their function is. So for example, with this hammer, the material it's made of, the color, doesn't matter, right? That's not what tells me what it's for. What tells me what it's for is its shape. And that's why I've developed this word that represents its shape, that encodes its shape, right? And its use at the same time. So in this models as mind approach, we initially use models as our object of study to establish these types of causal relations that we think may exist. For example, the need to distinguish shape is what leads to us having a shape bias in our system. But how do we then go from model to mind? How do we then go from talking about models to humans? Well, we might have hypotheses that this type of causal relationship could also exist in people, right? So maybe this need for shape distinction in people is driven by the importance of artifacts. And what our causal models give us is that they then give us testable predictions. So if artifacts are in fact as important as they are for people and what are driving this need, then we have two predictions. The bias should be strongest when objects in experimental settings are expected to be artifacts rather than, say, natural kinds. And second, that the bias should be strongest in societies that have access to more artifacts than societies that don't. Turns out we have evidence for both of these predictions. So the bias is really strongest when things are assumed to be artifacts, and as soon as people think that they are natural kinds, it disappears. So if I tell you this is a fruit from an alien planet and it's called a loman, and now I tell you there's another one, here, your shape bias will likely have disappeared. That's because fruits tend to not necessarily have this shape bias, right? It doesn't make so much sense to have a shape bias with something like fruits where shape doesn't matter that much. And then we also have really new evidence that it is actually strongest in societies that have access to more artifacts. So there's studies that have compared the shape bias in American English speakers versus speakers of Tsimane, which is a language spoken in Bolivia in rural parts in the Amazon. And there, Tsimane speakers have little to no bias when it comes to the shape bias in these experimental settings. So in this models as mind approach, we were able to show that there was this causal relationship that exists for our neural agents, and that the shape bias followed from this high communicative need for shape distinction. And given this prior and outcome setup that we've come up with, we were able to hypothesize that something similar existed with people, giving us testable predictions. Once you find evidence for that, for those testable predictions in people, you can then actually generalize that causal relationship also exists in people. And that's really cool. So in the models as mind approach, in this particular case, we're again able to learn a bunch of really cool stuff about people. One of the things we learned is that human learning biases can emerge because of social needs and how we interact with the world. So they're not only innate biases, what you might think of as biological biases, or data biases, what you might think as the biases that naturally exist in the data in the world, but that they can also emerge with how we actually interact with that data in the world. So a little more about that. So if you think of this as real information, us as AI scientists, often when we try to design models and data sets, we try to make our data sets real world approximations, right? We try to have unbiased samples of the information that we find in the world. But the problem is, recently, more and more, we're finding evidence that human learners are not unbiased samplers, but actually don't necessarily experience the world in a uniform way. They have biases that appear either because of their innate biases, because of the way they interact with the world, that actually lead them to experience the world in a really unbiased way. And so it's important for us to understand these biases, both so we can understand how people are learning, but also because maybe we want to think about having models and data sets that are in themselves biased or biased samplers. Okay. So that was my models to study people, talked about models as tools and models as minds. Now we're going to do a little shift, right? So I talked initially about there being two directions. First, this direction where we studied how models could be used to study people. But now I want us to talk about this other direction, how we can take what we know about people to help inspire our model designs. So let's talk about cognitively inspired models. Okay. Well, let's sit before I continue. Okay. So I'll start by saying that cognitive science and AI have been intertwined since the start, right? Neural networks themselves as an object of study were in many ways inspired by the human mind and the human brain, right? And I think it's important to note that many seminal ideas in AI, especially recently, take a lot of the roots from cognitive science, be it distributed representation, this idea that you can represent words as a combination of features or values, not a new idea. That we should have recurrent word processing, that we should consider words in context in a linear way. Also an idea from cognitive science. And finally, even things like attention mechanisms, at least in the causal LM approach, take many of the roots in cognitive science. So when you put all of these things together, you scale them a bunch, that's how we get things like large language models, right? And so in many ways, cognitive science is seminal to a lot of the discoveries and developments that we get in AI. Now, one of the places that I'm really interested in working in, part of a larger community, is sort of discussing some of the differences that still exist between these models and how we think about learning in cognitive science, is what we call the data gap. So, human learning requires a lot less linguistic data than our language models currently require. And I'm interested in working on how we might sort of remedy this if you think of it as a shortcoming. Might not be a shortcoming for all uses, but if you're interested in trying to develop more data efficient and energy efficient ways of learning language, how we might do this. So one of the places that I've got ongoing work is on designing language models that induce hierarchical structure over language as they're learning. And I'm interested in looking at whether or not these help explain human data better than regular language models, for example, but also whether or not these types of models can be more efficient learners if they're able to generalize from a lot less data. And this is all, I'm also looking at this in the grounded context as well. Speaking of grounding, beyond word learning per se, we can also think about how these types of approaches could also go for more complex reasoning and problem-solving tasks. So I'm also interested in looking at, in visual grounded language models, how things like logical, spatial, numerical reasoning skills emerge, and whether the types of skills they develop resemble the ways that humans have these reasoning skills. For example, if we take spatial reasoning, there's an absolute way to think about spatial reasoning in the sense that all the things that are behind that line are behind this gray square. But there's also more of a gradient way of thinking of it, and this is how humans think of it, which is the thing that we have a sense that certain things can be more behind than others, right? So the gold ball is more behind than this blue cylinder, right? And so is it possible for models to develop those same sort of gradient representations and understandings of these concepts? And I find that they do, at least in the visually grounded setting. I've also found early evidence for things like pragmatic reasoning. So whether or not models are able to develop the ability to think about alternative expressions that could have been said in a given context as a way to change how they might actually interpret words in that context. So we'll take an example of like logical reasoning. So if I give you this image and I say how many objects are either cylinders or red things, depending on how you interpret or, your answer will either be 4 or 5. There's not really a right answer here. It really depends if you think of or as being inclusive or exclusive. So are you including things that are both red and cylinders? And so models will actually, at least I've got early evidence that they actually consider whether or not you could have used and in a context like this, and this will change how they interpret that word in that given context. Okay, so to recap today was about connecting cognitive science and AI, and I talked about this being a two-directional thing, both studying models to help us understand how humans learn and reason, and then on the other side, thinking about how we can take what we know about how humans learn and reason and see whether or not that can help us inform our design choices when we design AI models. For the models to study people, I talked about two approaches where we use models really as our object of study. So models as tools and models as minds, and we looked at 2 case studies. I hope that I was able to convince you that AI models are actually really useful tools for helping us to understand the human mind, and that vice versa, that in many ways we can take inspiration from what we know about the human mind as a way to hopefully inspire our next discoveries in AI as well. So on that, I'll say merci. Any questions?
Hi, Eva. Thank you for the talk. I guess one question that I was thinking is, you know, many studies where the shape bias has been validated on different sensory inputs like text or pure auditory rather than visual information.
Interesting. I don't know of any studies, but that would be really interesting, like where you'd have like a textual description of an object.
Yes, exactly.
Oh, interesting. I don't think that's ever been done, no. That's pretty cool though. That's an interesting idea, yeah. Because that would suggest, like if you were to find that it didn't exist in the textual setting, it means that there's like biases that are really coming from like the visual encoding and the visual space being joint with the text, and that'd be very cool to see, yeah.
Yeah, it's in the higher settings.
Mm-hmm. Cool, yeah.
Abdul-Razak, if you want to ask your question, you can go on. And then Zoe can go ahead.
Yes, I have a question. I'm actually not really familiar with psychological aspect of language learning, but I was interested to know if this research tries to map the psychological reality of language learning to what we have currently in language models in machine learning, or it's the other way around. Thank you.
Yeah, I think it's a bit of both, right? So so I'll say this. So neural networks have been used in psychology for a long time to study as cognitive models, to study human learning processes. So there's a whole movement starting in the 80s called connectionism that posited that we could use neural networks as approximations for the mind and use them to study human behaviors like language learning. It was very popular for studying language learning. But the thing that we're presented with, as you kind of hinted at, is that since then, the way we develop our models is no longer as cognitive models, but instead we're kind of developing them really from an engineering perspective, and we've really moved away from that initial inspiration. And so, at least from like a scale point of view, there's no way that we could actually really consider these models cognitive models per se. And so I think there's now like with researchers like myself and some other researchers, there's kind of a revival of trying to figure out if there's interesting ways that we can still use these models to help us answer these questions that we have in psychology and in cognitive science without needing to make that leap of considering them cognitive models. So that, yeah, there is work doing that. I would say it's pretty new. It's a pretty new idea, but it is one that's growing in popularity. And as I mentioned, the other direction, yeah, that's been around since the beginning of AI time, where this idea that we can take inspiration from how we encode information in the brain as a way to inspire how we design our models. Does that answer your question?
Sorry. Yeah, thank you so much.
Yeah.
Yeah, hi. Can you hear me?
Mm-hmm.
Okay, yeah, so my question is, if you go back to your slides where you compare the surprisal between the function words and nouns, also between children, I was wondering, like, for language models, because these nouns or function words, they're all described in a textual way. There's no way for them to be grounded. So are they like just abstract as you know what I'm saying?
Yeah. So I think for one thing, function words are often the ones that are learned the latest by kids, and that is very likely because of what you're hinting at, which is that they tend to be really abstract, and sometimes they have multiple meanings depending on the context in which they appear, right? So things like, let me think. Yeah, like all can both be a pronoun, meaning a group of people, but it can also be a determiner to sort of quantify a quantity, right? And so, yes, I think that you're right in that the fact that they're abstract and means that they are harder to learn as well. In these studies, we control for that, but that's definitely like a true statement, and we have evidence that that's the case. That abstractness definitely needs to learn them later. Yeah.
Okay, so another follow-up question is: do you think that current large language model requires so many training examples or so many let's say just training examples? Is that because the pure even for nouns, they need a lot of examples to understand the relationship between the nouns and other words, because there's no grounding, and therefore large language models also need so much more training examples than human children.
Yeah, I think that's a really good hypothesis, and one that I think a lot of people would agree with, which is, if you get the visual grounding, maybe it would help. I know that people are trying to do that, and it doesn't always work as well as we'd hope. I'm actually of the opinion that there's a little more going on there with kids, and that's that I think kids don't have a simple objective function. I think that we are actually trying to jointly learn multiple things at the same time, and that when you have these sort of joint objectives that are intertwined in some way, you get these biases that come out where you end up kind of constraining the learning space in different ways, and that those constraints are what allow us to learn these things faster. And so I think that it's a mix of things. It's both that human beings get a variety of different inputs in terms of the types of inputs, so visual, social, embodied, sound, and so on. But we know that it's possible, obviously, to learn language without seeing, right? There are blind people that learn no problem as well, and it's also possible to learn language without hearing, right? So it's not just about, I think, the input and the grounding. I think there's more to it, and that the more to it part is what really interests me, which is around the fact that there's probably joint learning objectives happening here, and that out of those joint learning objectives, we're developing all sorts of learning biases that emerge over time and that help us learn. Yeah.
Okay, thank you.
Yeah.
Yeah, thank you for the talk. Yeah, it's a bit of a question. There's two main differences, when kids learn language in models like that. Kids can't read, so they don't have access to words. So I think for functional world, it's unlikely that a functional work themselves.
Mm-hmm. Right.
And so, how do you think we could simulate the fact that we just have access to speech and text, and also the fact that most of the time it's not interaction, not just like being exposed.
For sure. So this is obviously a simplified problem, as you point out. We're already giving them word boundaries, right? And we're taking out the sort of social aspect where we're not necessarily considering what they answered in context. I think in terms of the word boundary thing, we're obviously simplifying the problem, but we do have, not in this case, in this experimental setup, but we do have evidence that actually the initial evidence we had that kids track co-occurrence statistics is from how they determine word boundaries. So there's these studies from like the 90s that have shown with invented languages that depending on the co-occurrence of syllables, babies will learn to like recognize which syllables are actually represent groups that come together often and sound like words versus the ones that if you put them together sound like gibberish to them. So I think you could, in some sense, generalize this process to just a smaller unit of meaning if you wanted to, and see if you could go beyond just the word and look at like syllable and so on, so even like smaller tokens. You could also ideally start from sound, but we know that that's pretty difficult right now. But ideally, I would love to, later on in my career, if we get to a point where we could just like take in sound, take in video, and do the same setup in a much more realistic setting, it'd be really cool to do that. That was your first point about word boundaries. What was the second point?
Interaction.
Oh, yes. So the interaction part. So, I kind of get to that interaction part a little bit in the second experiment where we have these setups where we've got agents that are interacting, but it's not embodied interaction, right? It's one where we've got visual and language input, but not how these agents interact with one another physically in the world with the objects they're talking about. I know there's like some preliminary work trying to sort of mimic this idea of embodiment out of like DeepMind. Like Felix Hill has kind of looked at some of this and how we learn in these embodied contexts. But I think that would be, a good direction initially. If we wanted to model this in like an interactive embodiment setting, would be to consider how you could have these agents learn in like a virtual world. And eventually, obviously, it'd be cool to do robotics as well, but I don't think we're there yet either. Yeah.
Hi. Thanks for the talk. Can you hear me?
Yeah.
Okay. Thanks a lot for the talk. I had a question about the baby LM stuff you were talking about. Jackie and I, we worked on a submission as well, and we ended up really just doing fancy pre-processing to get some better results. So I was wondering if you think that there's some sort of inherent limitation in that challenge and just in general where, if you don't inject any other type of data, then you're sort of bound to not be able to close the data gap that you were talking about.
Yeah, so I know not everyone knows the Baby LM challenge, but I'll talk about it. I do think there are a bunch of inherent limitations to that challenge. For one of the biggest ones for me was the fact that it was limited to transformer architectures, which definitely limited certain things. And then they did have the like open version where you could include other types of input, like visual input and stuff, but they didn't have like a mapped data set in particular that you could use. So I didn't look too much into like what the submissions were in that open setup and what they were able to do exactly. But I do think that, it'd be really cool if in future years the Baby LM challenge grew to allow for like data sets that were more grounded, and if it also grew to allow for different types of architectures if people wanted to kind of explore developing other stuff. So I also did a submission, and because we had to have it as a transformer, we ended up doing like a grammar induction thing and then using that as like pre-trained embeddings for a language model, and that's not ideal. Ideally, you'd want sort of something that was kind of integrated, and we found that though it helped, it didn't help as much as we wanted it to. There were definitely some limitations to that challenge, but it's the first year they do it, and I think from all the submissions, the solutions that seemed to work the best were those that did like a bunch of data pre-processing or did some sort of like filtration of the tasks and data and stuff. And so if they want things to be actually interesting, I think, yeah, we're going to have to sort of lift some of those limitations.
Great. Yeah. Thanks a lot.
Yeah.
Hey. Yeah, great talk. Thanks so much. I had a question about embodiment. So we already have pretty powerful language models, and like just learning purely in isolation without any embodiment. And I just wanted to know how you see embodiment. So like, once we start grounding this, uploading our language models to robots and having them interact with the real world and associate all these words with real concepts like sensory inputs, how do you think those models are going to be better, or how are they going to be different than what we have right now, for example, with like GPT-4 and such?
Yeah, that's a really good question. I honestly, I don't know, and I don't think that like just loading a language model into like a robot is necessarily going to work as well as we hope. Like, I think there is a part of it, at least from the human perspective, where the grounding has to start from the beginning. And so I don't know exactly, that's going to involve a bunch of like our RLHF, but with input from the actual interactions of the model post hoc, and I don't know how well that's going to do. It'll be interesting to see. I think another kind of thing you kind of hinted at is this idea that like even just from linguistic input that these models are getting, they're showing behaviors that kind of at least surfacely suggest that they like understand and that they are finding certain, I don't know if it's not exactly grounding the way we're talking about grounding, but that they're able to kind of create connections and maps of information that allow them to sort of build these connections. And I think that's really fascinating and something that a lot of cognitive scientists right now are kind of diving into, right? Is trying to understand, like, do they understand even without grounding? And is it enough to just scale and scale? I don't think we have an answer for that yet. Because there's clearly, certain places where they have shortcomings, where they may, reason actually kind of differently from we do. But whether or not that counts as reasoning is also an open question, right? You can think of animals as thinking differently than we do and reasoning about problems maybe differently than we do, and maybe it's something similar with these. And so, yeah, I think that's a really fascinating open question. Obviously, I have concerns around this idea of like bringing LLMs into the world and giving them embodiment and giving them all these things. There's a lot of social concerns around that, what will happen to the world and so on. But I don't think it's necessarily going to be as like easy as we think, and it definitely won't be that they will necessarily create the same groundings that we do, given that they're not doing it from the start of learning and learning it the same way we do. Does that make sense?
Yeah, great, thanks.
Yeah.
Thanks for the great talk. I have a quick question. It's interesting to see how the bridge between AI and cognitive science was like going from how we see less surprisable words being learned faster by kids. But what do you think about going from cognitive science to neuroscience, where less surprisal, or rather more surprisal, generally means dopamine-related learning systems? Do you have an idea of
Interesting.
A non-dominant dopamine learning system in kids, which gets dominant?
Yeah, interesting. Okay, so there's these effects that they call the like Goldilocks effects in kid learning, meaning that kids kind of like the like just right middle, where they don't want something too surprising when they're learning, and they don't want something too easy either, in order to kind of like keep their attention. So we see this in certain experimental settings, like this is like babies, they do these head turning paradigms where they try to get babies' attention and see how long they can hold it. And so maybe this is interesting, because maybe what's going on here is that initially, with these age of acquisitions, this is sort of like it's a process, and it's linear. Like we're taking them as like an order, whereas with these surprisal values, I'm averaging across time, right, and across sentences, and so we're kind of losing this sense of like surprisal at different ages. And so ideally, I guess, to sort of test this hypothesis of like, do they show these sort of same Goldilocks effects where we would expect like surprise, somewhere kind of in the middle. You'd kind of have to look at over time. So if you had like we don't have this type of data. If you had transcripts that you could tag for how old they were and you had enough of it, and you could train a bunch of different models and see whether or not those surprisal values are changing over time and seem to kind of show the same effect where the words they learn initially in the uses they use have this kind of middle ground, and then that changes over time as you use them. So yeah, that would be my answer to that. But yeah, given that we don't do that right now and we're kind of mashing everything together and averaging it, we kind of lose the ability to see that. Yeah.
Hello. So I had a question on like, I heard you said something about Mandarin being different than English. They learn sort of nouns first to focus on predicates.
Yeah.
I was curious to see like what would be the effect of like bilingualism and learning more than one language at a time for like babies. And if you could like, if there is a difference in like the age of acquisition, would that also be like a thing to do for language models?
Yeah, interesting question. So obviously I don't have data for bilingual speakers. Generally, what we say about bilingual speakers is that their vocabulary development tracks with mostly monolingual speakers, but it's when you count across both languages. So if you were just to kind of take like the semantics of the words rather than the specific words, you may, I assume, probably see the same patterns where if, we're talking in Montreal, so you've got a bilingual English Franco speaker, they might say le, but they might say wolf, but you would see those relative to one another across languages probably having the same pattern and the same ordering effect, just that you would have to sort of consider their vocabularies across both languages. I think that's probably what you would see, given that we know that like vocabulary development seems to track. You just have to kind of calculate over both. So they have fewer words in English and fewer words in French, but if you put them together, they have about the same as someone just learning French or just learning English. Yeah. Does that answer your question? Okay.
Let's thank Eva again.
Thanks.